Hello friends, welcome back to my YouTube channel. This is a continuation of my discussion on tall column. This is part 4 of that discussion, and today I will be continuing my analysis of stresses that are induced in the wall of a tall column. And today specifically I'll be talking about stresses induced due to wind load. In my earlier parts, in part 1 I have introduced tall columns. Then I have talked about the stresses that are to be considered while designing a typical tall column. In part 2, I have discussed stresses that are induced due to internal pressure, external pressure, or vacuum. And in part 3, I have talked about the stresses that are induced due to various dead loads associated with a typical tall column. ठीक है, so to begin with, let us understand various stresses that are induced in the wall of a typical tall column. First, we will know the loads that are responsible for stresses. So, loads due to which stresses are induced. Let us understand. So, you have internal pressure, external pressure, or vacuum. So, under the influence of these loads, longitudinal or axial stress will be induced in the wall. Also circumferential or hoop stress will be induced in the wall. So these stresses may be tensile and compressive. Then due to dead loads, again longitudinal, that is axial stresses will be induced, and this will be compressive stresses. Due to wind loads, again longitudinal stresses will be induced, and this will be tensile and compressive. Eccentric loads, they will induce longitudinal or axial stresses in the shell wall, and these will be bending stresses. And then under the influence of seismic loads, the longitudinal stresses will be induced in the wall, and this will be tensile and compressive. Okay, so these are various loads that will act upon a typical tall column, and that will cause stresses in the wall of that column. In this particular lecture or in this particular video, I'll be talking about wind loads. We are going to understand how to get stresses that will be induced due to wind loads. So these are longitudinal stresses, and they will be tensile and compressive in nature. Okay. First, let us know how to get the wind load, how to calculate wind load. Unless and until wind load is not obtained, we will not be able to get the stress due to that wind load. Okay, so let us consider a typical column whose outer diameter is DO, which includes the insulation also if it is an insulated column. So DO represents the outer diameter, which also includes diameter of the insulation if it is an insulated column. Okay. Then we are going to consider, let H be the height of the column. So for such column with diameter DO and height H, the approximate wind pressure in Newton per meter square is given by this empirical equation. Pw is equal to 0.05 Vmax square, where Vmax is the maximum wind velocity under worst weather conditions in that particular area, and this velocity will be given measured in kilometers per hour. So this equation Pw is equal to 0.05 Vmax square, it gives wind pressure in Newton per meter square. Now Vmax, this velocity, it is going to change with height of the column. Vmax near the ground is less as compared to the velocity away from the ground. So Vmax near the ground is less than away from it. For columns with heights that are greater than 20 meter, we need to consider it in two parts. So for columns with height greater than 20 meter, the height is considered in two parts. Which are these two parts? The first part, it covers a height of 20 meter from the bottom. So if you measure from the bottom, so first part of the height will cover a distance, cover a height of 20 meter. First part covers a height of 20 meter from the bottom, whereas the second part, it covers a height of the height that will be above 20 meter. So part 1 will be height up to 20 meter, and beyond 20 meter, that will be considered as the second part. So in this typical diagram you can see up to height of 20 meter, we will be considering the first part. Let us denote that height by HB. Then the other part, that is height above 20 meter, let us denote it as HU. So here we have understood that if the column is greater than the height of the column is greater than 20 meter, then height will be considered in two parts. First part we will be considering 20 meter out of the total height, and remaining height will be the second part. Okay, and then wind load will be acting in this way. So on each part, the wind will be acting uh, uh, uniformly. There will be uniform distribution of load. So for first 20 meter, and then for the remaining height as well. So near the bottom, wind pressure is less, the velocity of the wind is less as compared to that in the at the top of the column. Okay. So now let us continue with this discussion. Now each part is considered to be a uniformly loaded cantilever beam. So if you look at the bottom part, you can see the wind load is uniformly acting on the column. So this part can be considered as a uniformly loaded cantilever beam. Same is the case for the upper part. Upper part is also considered as a uniformly loaded cantilever beam. Now force on the lower part due to wind pressure, it will be given by this equation. It will be given by this equation. Now FWB, that is force acting due to wind on the bottom part, is equal to K1 into K2 into PWB into HB into D0, where K1 is coefficient that depends on shape. It is 1.4 for flat plate, and it is 0.7 for cylindrical surface. K2 is coefficient that is depending on the period of vibration. Let us denote it as POV. So if POV, period of vibration, is less than equal to 0.5, then K2 is 1, and if period of vibration is greater than 0.5, the value of K2 is 2. Okay. PWB in this equation will be obtained by the empirical equation which we just saw. PWB will be equal to 0.05 V max B square, velocity, maximum velocity in the region under worst condition at the bottom. Okay, so with this all values, you can use this equation to get force acting on lower part of the column due to wind pressure. K1 is coefficient, K2 is another coefficient, PWB is given by this equation, HB is height up to 20 meter, so you can say HB itself is 20 meter. If it is less than 20 meter, then you'll have to use that value, and DO is the outer diameter of the shell, outer diameter of the column, which also includes the insulation diameter in case of insulated column. Vmax is wind velocity at the bottom. Vmax B is the wind velocity at the bottom. Then force acting on the upper part due to wind pressure, again it is given by a similar equation. So FWU, force due to wind acting on the upper part, is equal to K1 into K2 PWU HU DO, where K1 is coefficient that depends on shape, and it has the same values as understood earlier, 1.4 for flat plate, 0.7 for cylindrical surface, and K2 is coefficient that depends on the period of vibration, that is POV, Again, it is 1 if PU period of vibration is less than equal to 0.5, and it is 2 if the period of vibration is greater than 0.5. PWU will again be given by the same empirical equation. PWU is equal to 0.05 V max U square, where V max U is the maximum velocity at the top of the column. So this equation will give you force acting on the upper part. In this equation, HU will be the height that is greater than 20 meter, and DO is outer diameter, that includes the diameter of the insulation as well. Okay. Then wind pressure, uh, uh, this wind pressure acting on at the bottom and wind pressure acting at the top, in different areas, what are the values? Let us see. In coastal areas, wind pressure acting at the bottom is between 0. 0.7 kilonewton per meter square and 1 kilonewton per meter square, whereas wind pressure acting on the top of the column is between 1.5 kilonewton per meter square and 2 kilonewton per meter square, whereas in areas where there are moderate winds, uh, wind pressure acting on at the bottom is 0.4 kilonewton per meter square, and wind pressure acting on the top is 1 kilonewton per meter square. So these are the values values of wind pressure in different areas. Now let us talk about the bending moment, calculation of bending stress due to wind load. So bending moment at the base of the column is given. So for columns with height having whose height is less than equal to 20 meter, the bending moment will be given by this equation. Mw is equal to Fwb into h by 2, and for column with height greater than 20, Mw will be given as Fwb into hb by 2 plus Fwu into hb plus hu by 2, where Fwb and Fwu are the forces that act on bottom part of the column and top upper part of the column. We just saw equations for them, and then this bending moment is going to produce bending stress, uh, and this bending stress is given by this equation. Fwb, that is bending stress under the action of wind, is equal to 4 mw, the bending moment, divided by pi into di plus ts into di, where di is the internal diameter of the column, ts is thickness of the column, and mw is the bending moment that is to be obtained using this two equation. If height is less than 20 meter, mw will be given by this equation. If it is greater than 20 meter, it will be given by this equation. Okay, so this is the bending stress. Now if you consider a plane at a distance of x from the top of the shell, so we are talking about this distance, then uh, again this distance is selected in such a way that the thickness of the shell is uniform with this. So wind pressure acting at the plane is given by the same empirical equation. Pw is equal to 0.05 V max square. Load due to Pw will be given by this equation. Fw is equal to K1 into K2 into Pw into x. Now this time, since we are considering a distance of x, x will come into that equation into d0. Then bending moment, we are talking about bending moment at the plane x, it will be given as mw is equal to fw into x by 2. Okay, and then this bending moment will result in bending stress, that will be given by this equation. Fwb is equal to 4 mw divided by pi into di plus ts into di, where mw you are getting from this equation. Di is the internal diameter of the column and ts is the thickness of the column. Okay, so if you do further analysis, so you just got equation for Fwb. Fwb is equal to 4 mw into divided by pi into di plus ts into di. mw is given by this equation we just saw. It is fw into x by 2. fw in turn is given by this equation k1 into k2 into pw into x into do. So if you use first equation for mw in this equation, you get fwp is equal to 4 fw into x divided by 2 into pi into di plus ts into ts plus ts into di. And then when you use equation for fw, you get this expression for fwb, that is stress due to wind at the bottom. So this will be a bending stress due to wind pressure. So this will be 4 k1 k2 pw x square do divided by 2 into pi into di plus ts into di. Then the period of vibration, in order to calculate values of k1 and k2, we need to calculate period of vibration, and period of vibration is given by this equation. Period of vibration is equal to 6.35 into 10 to the power minus 5 into h by di plus ts into w upon ts, where h is height of the column, di is internal diameter of the column, ts is thickness of the column, w is weight of the entire column, that is weight of the shell, weight of the insulation, weight of the attachment, weight of the heads, and ts is thickness. So w represent weight of total weight of the column, which includes all the weights. K1 is 1.4 for flat plate, we have understood. K2 and for cylindrical surface K1 is 0.7. Then depending on POV, if you get it less than equal to 0.5, K2 will be equal to 1, and if you get it greater than 0.5, K2 will be equal to 2. So in this way you can get values of K1 and K2 and then use in this equation to get the bending stress that is due to the wind pressure acting on the column, acting on the height uh, part of the column up to a distance of x from the top. Okay, so with this I end my discussion on stresses that are induced due to wind load. So we get this bending stress that comes into picture due to the wind load. So thank you for watching my video. Thanks for watching. Do subscribe to my channel. Tell your friends to subscribe to my channel, and be with me in future to know more about chemical engineering. I'll be discussing more about tall columns in my coming videos. For now, have a nice day. Bye bye. Take care.